Good morning to one and all. My name is Shankar Shukla. I'm from IIT Roorkee, first year student, and today I'm going to present my rocket designing, which I have done using Open Rocket software. I have designed this rocket for meeting the criteria mentioned in this competition by Helium Learning Lab. So, firstly, we will see what are the different criterias which were mentioned in the competition. So, yeah, these are the different criterias which are mentioned in the lesson plan. So firstly, we have to have a minimum 1000-meter altitude, and we have to use single stage rocket using only G-class motors, and we should have a payload of 50 grams, a minimum. So here, I guess I'm going to increase my payload to 150 grams, and I'm going to use two propellant. So I'm going to use two engines, cluster of two, and yeah, these are the keeping in the mind the maximum weight of rocket this much and propellant weight of 125 in this. I'm going to design my model. So yeah, so let start modeling our. Okay, I'm going to start making my rocket keeping in the mind the criteria which were given to us. So basically, we have to keep in the mind that we have to maintain our stability uh, near to 1, means it should be not less than 1, it should be more than 1 or 1 and less than 2. So yeah, now we are going to start our modeling. So here I'm going to first select a nose. Yeah, and I'm going to use nose just for aerodynamic purpose. I'm not going to fit any payload in it. So I'm going to use very small cone, and I'm going to use a power series because it has a very less drag. I'm telling this because I have done many demos using various of uh, shape of cones, and this gave me a minimum drag giving a high altitude. So I'm going to shape my parameter. 0.5 is okay. Nose length I'm just going to keep only 1 inch. Then I will go for base diameter. I need a minimum 3 inches so that I can fit my motors within the criteria. And I'm going to use a thick wall. Field for the time being, we will use a field one. And if we don't meet a criteria, we will change it. And as known, nose cone experience a very uh, high interaction with the molecules. So keeping in that mind, it should go through the cutting through wind. So I'm going to use a very strong material, fiberglass. So there should be a no big deal with the strength of the nose. Then shoulder, I'm going to, okay, diameter should be bit less than 3 because I've used the 3 inches for the nose. Length I will keep just again 3 inches only, just to fit it into our um, main body tube. Thickness I will keep it only 0.1. I will keep it end cap. I will tell you why I'm keeping it at end capped interval. I'm not going to override anything. Okay. So now I'm done with the cone. Now you can see the CG stability is 0, means less than 1. So you have to keep it in the mind to keep the stability near 1. So now we are going to add our tube. Our tube should be of length. Our body tube length, I will keep it as 23 only. I have tried many different length. This where so I'm directly entering best results which I have used. Not going to automatically. I want to modify according to myself. B 3 in a diameter 2.9. 2.9. I don't want a much thickness, so I will reduce the thickness here. Okay. And yeah, the cardboard will be not a very good choice, so I will change into PVC pipe, which is also easily available. So yeah, we are building this rocket mainly, which can be easily to build and can be made for various purposes. So yeah, this is a PVC. Okay, I don't want any override. So yeah, so now I will go for inner tube, where I'm going to fit my motors. I want to using a cluster of motors. So firstly, I will define my auto diameter according to the motors which I'm going to use, which will meet my criteria. To increase this length, position should be is okay. Now just cluster, I'm going to change to double. And I will doing this setting. Then I will use engine blocks. So these blocks are to stop the motors, as we can see, for moving forward into this tube. So I'm going to use this engine block. Yeah, this is calculated automatically. 0.3. I want to decrease my, what is okay now. And yeah, I will shift my mount to little above. This bit above. I will keep it 4.9 only. Okay, okay, done. And then I'm not going to override anything here. Appearances is also automatically default one. Now I will, the key part I'm going to use is Now fins, which fins, not trapezoidal, or I'm going to use elliptical or freeform. I'm basically going to use elliptical fins because this has a minimum drag coefficient. Means using this elliptical fins, we can minimize the induced drag due to its geometry. So I have used this basically on its geometry, and using only three fins. This also helps in reducing a drag which if we increase fins, the drag may increase. So three fin is optimized one. We are going to only use three fins, and now we are going to fix its root chord, and its height also 3 inches. That is sufficient. So now we can see how drastically our stability has changed from has gone near to 2. It is also very much. Yeah, it will decrease further as we build it. Pin tabs. I will let it calculate by itself automatically, and it will adjust accordingly. Oh, tab position has not been changed, so I will override it and I will change it to 1. I think so. This must be okay. So I guess pin tabs are in position. Mm, Now I will give a structural strength to my fins and this uh, boosters, as it cannot be held by itself. So I will attach a central ring. Central 2.9, it has calculated automatically. 1.2, yes, it is again. But I will want a bit more thickness to provide it a structural strength. This might work. And then I will also like to move it bit above. Minus 0. This one should be sufficient. Yeah, this one was what I calculated before. Again, I don't want to override this to calculate our. So now again, I will add another one to support upper side. Again, this also should be a same parameter. I will move it further to a little above. Yes, now it is okay. I guess I have to change and tab. Yeah, we can see it has calculated and adjusted between these rings. So now, yeah, this is okay now for me. Now structure here, my fins and my boosters are now okay. Now I have to add some safety features to my body tube. So now I will add this shock cord. This will provide me a better stability during my ejection time. So I want bit a long shock cord. 200 inches will be sufficient for me, and the position should be just below my a cone easily can observe. Yeah, I will increase my length also. You can see these are the different parameter which I have set, and you can see now my position of shock cord. Okay, now we are cool. We are done with shock cord. Now we will go further to add a main component for recovering our this body, main body, using parachutes. So I will use a parachute during my recovery. Hmm, my diameter, parachute diameter should be, yeah, sufficiently big. So it has a round hit velocity. I will not play with this drag coefficient as it is. Okay, this should be on 14. 2 will be sufficient for the small rocket only. I'm not making a very big model. Small, sufficient to meet my objectives. I will move it a little bit down. So not very close to, yeah. Okay. And I will increase the length and the diameter so that it can be easily fitted in my tube. Okay, done. Nicely done. Yeah, the main thing is which material should I use. This so I will use, yeah, this only. So this will be sufficient to have a minimum ground hit velocity, so it can be easily recovered. And this also should be a bit better quality, so I will go for 11 inches nylon. Good strength. So yeah, so nicely done. Okay, I guess that my injection should be at apogee. After coasting time, it will reach maximum apogee, and then I will be able to eject. So from there and have its downward trajectory. Yeah, done. Now I will like to add. Okay, I will add payload. Yeah, payload was 50 grams was a minimum criteria. Payload. It was 50, but I want a big mass now, as there is no 50 grams, not much equipments I can carry from different activities. So 150 grams can be sufficient to carry on different activities at that altitude, or instruments which we can use for measurement of various parameters. So 150 grams is sufficient, I guess. I will change the density. I don't want very dense. Diameter I will keep little big, which can be easily fitted. Okay. Let me change the position. It's not as I am going to fit it in my tube. I don't want it in my nose section. So yeah, this is good. Above parachute. So as the charge will be ejected, my payload will be ejected from here. Parachute will be deployed, and we are safe to go. Okay. Okay. As I have to build a pressure here, so I will again introduce one more inner tube. Inner tube. I will adjust the parameter, so I can guess. So these are my calculated parameters which I have calculated for the best position to build up pressure. Pressure distribution. So this now to give a structural advantage, I will use. Oh, let me check which material which I have used. Cardboard, yeah, okay. This should be not a problem. Now a central ring. It has automatically calculated. Just I will change its position. So I want little higher. So I will go for, yeah, this might work. Yeah, this one is what I calculated. These are my backend calculation which I have done for meeting my criteria. Now let's go for one more to give it a better stable structural benefit. Adding one more. Again, I have added, not inner tube, sorry. I will go for ring. Where it is, sorry. Yeah, again it has calculated. Just I will change its position. Should be minus little above. Yeah, this was the best position which I have calculated. Now you can see, now I have a nice structural pressure distribution inner tube which will direct the pressure hot gas ejected from here to the my parachute and my payload which will be deployed after reaching my apogee. But yeah, this will be the hot exhaust gas, so I have to keep some protection here. So I will add some type of material to protect it. So I guess I will add mass component only. Pending. Yeah. 5 grams can be well sufficient to protect. Mm, I don't want such a dense also. I want just to mainly a cotton feeding, so it cannot damage mm, my parachute and my payload. Keeping in the mind, I have fixed this parameters. I will increase the diameter also. As my diameter of tube is 3, so I will keep it 2 just to be safe. I will increase its change its position. Just you can see now. I've got a better position now to protect my this. Okay, let's change. Now I have 5 grams, and you can see my position. So yeah, ready. Almost I am done. Now you can see I have a stability of 2.5, and I'm not enter the motors. So I have used inner tubes. New configuration. So as it was mentioned, G class. So we are going to use G class. Which will meet our criteria. So these are different G class motors. Let me see. So as you can see, we are having, okay, we can use this one. 5.5. As you can see, 65.5 is empty mass and launch mass is 128 grams. So we get a difference of 62.5 and multiply to 125. We can see our propellant is of 125. So yeah, this is a criteria which, yeah, we are satisfying here. Now, yeah, this must be a last part. Okay, or I will see I can use any other. Here payload, this will increase. So I guess this is sufficient. Okay, sufficient. Now we can see we are having a just a 3,600. It's not near 1,000 meter. And now stability we are having, yeah, great. We'll also bring it to the one. What we can do extra? So yeah, many rockets are just built like this way only, simple rocket. But to increase my altitude and to have a unique design, we can have a boat ending. Means we can have a narrow ending, which we can see in bigger rockets. They just don't have this vast opening. They try to converge and then diverge their propellant so that it can give a maximum thrust which can push it into the atmosphere. So similar, we will try to add something unique. So I guess, yeah, transition should work best. And yeah, this is automatically all calculated. As now you can see, my this has altitude has increased and my stability has gone bit lower to the one. And this is what we want. Conical shape, this is a perfect thing. So you can see after adding this transition, you can see how it has drastically changed. Now as it is managing with the thrust and hot exhaust substance gases. So I want a bit strong material to resist that heat, not melt and get fire, and which will result in my failure. So I will have a fiberglass. Yeah, this might work. So yeah, so I have did bit changes to bring my stability. This is my model which I have designed it before. As you can see, it is a similar, but I have bit modified it. So as you can see, it is meeting all the criteria. My motors are same. As you can see, I have done many simulation, flight simulation with different varieties of motor, and I have used the same. You can see G80, and my altitude has gone up to above 1000 meter, a bit above, and my stability has gone 1.02. And this is okay. Now it is exact the same model, which have you can see all the parameters. What are my body tube? This you can see weight is under the criteria. Different payload is inner. This is sorry inner tube. Payload is similar, 150 grams. You can see a transition. What I have put, I have put a fiberglass, and yeah, you have seen this same similar. It was I've just tried to make a similar model, and now you can see with few adjustment, I have adjusted my stability and my mass, and I have increased my this feet. So now you can. This is my simulation G80. So yeah, it's perfect. G80. I have used different motors, but this were going beyond the criteria. As I was getting a bit more altitude, the problem was with propellant and the motors. These are very high power motors and using a more fuel. So this has fitted well in this competition and giving a optimum result. As you can see, this is my apogee. Now let us plot different graphs and see what is my performance. So with time, velocity, let's see. Let's plot it. As you can see, yeah, my altitude velocity is now reaching here maximum. Yeah, you can see this the altitude vertical velocity. Now let's see vertical. Now let's see a drag coefficient, as it plays a very crucial role. Drag forces. Let's plot it. As you can see, drag forces for it increases. Now let me zoom in. It increases as velocity increases. Interaction with the air molecules also increases, and this drag also increases. Yeah, it goes till its maximum point after reaching near to apogee. After means after the thrust is over, it delays. Then it goes in coasting, and there is no thrust, and it goes and reaches apogee, and the parachute is shooted out, and we recover our model. One more thing, delay. What I have done is in this, I have to delay. It should be more than ejection of charge means what after propellant is burned, and there is some delay. Then the charge is ejected in the inner tube, and then our parachute and other things are deployed. So it should be more than minimum of minimum of 10-second delay to 10. So I will keep it 10, so it can coast further and have better altitude. So yeah, 10. So now we will see our simulation again. So you can see deployment we are having at 4.87 feet per second. this is sufficient, and ground hit velocity is should be near 5 meter per second. And yeah, this 16.8 feet per second, if we convert, it's near to 5 meters, means it is sufficient criteria to recover our body safely without breaking any parts. So yeah, uh, meeting all the criteria, I have built this model. It I have kept it very not too big, not too small, sufficiently sufficient for our needs. So basically, this payload which I have mentioned here, 150 grams, it can have many other devices to go in the higher altitude, and we can have a different experiment, a different measurement. Then we can collect tons of data going at high altitude and using it to our own benefit. And yeah, this is what a payload can do in this stage. At this not a very high altitude, it's just near 1 kilometer. So we can uh, use it for different experiment which require that 1 kilometer altitude only, and we can put in different devices for different measurement and collect the data, which will be sufficient and okay. And this can be recovered by various other, that is another part, can be done various other process. I'm not using this payload in the nose because as it is a small rocket and I don't want and as I don't have a second stage to boost it into further more atmosphere. So as nose have no more significance after reaching a high altitude, so I have not made it a very big nose. The reason, as we you can see, as we increase the nose, see, if we increase the nose, altitude decreases rapidly. See, if let me go a bit further, as you can see how the drastically altitude is dropping. So I'm not using because I don't have a main purpose or having a big nose, because it will increase my uh, drag contact with air and it will affect my apogee. So I will try to have a minimum amount of nose length to counteract the drag and make my rocket to cut through air and reach a maximum altitude and deploy the payload and the parachute and do further experiments which can be helpful for further uses. So yeah, this was now I can show you different views. This is my 3D view. You can see my parachute transition here, double thrusters. I have used a elliptical. As you can see, elliptical has a major role to decrease. As you can see, as it moves from away from the body, its contact of area with air decreases. So as above, it is having a high pressure and means you can see in aerodynamic we have a high pressure and low pressure region uh, around the fins. So as we go towards end, there creates a turbulent flow, which brings the instability in the rocket. So moving away from main body and decreasing the contact area with air gives a better stability, and which can be for our advantage. So we are having a converging shape as we move away from it. As it is not a aeroplane, it's not a rocket which moves at a hypersonic speed. It is in subsonic region only. So these fins are best to use in subsonic region. It is below 1 Mach only. As you can see, maximum my velocity is 742 feet per second, and maximum acceleration is in 20 G. That is sufficient, and my stability is near 1, which is mainly recommended, and not very near to 2, not less than 1. So yeah, this is the best uh, thing meeting the criteria we are having this model. You can see back view, already finished view, as we have used PVC, not a very big nose, small nose only, as you can have shown how drastically it changes my apogee. And this is everything what meeting my criteria. I have mm, modeled this rocket simple, small to meet my or any simple experimental setup which required is a high altitude measurements or devices which can. Okay, thank you. And this is that much only from my side. And building this rocket was very a great experience because I got into rocketry due to have knowing about Elon Musk. This made me more fascinated about rockets. Then this making this rocket, I have built tons of many demos. You can see this was my third demo, third no, you can say fourth demo, which is meeting my criteria. I have built various demos to test uh, different type, different shapes of rocket, and yeah, I have read different articles to meet this criteria. So from there, I came to know the different material which should be used to make a body, and yeah, and from there I have got a better knowledge of rocket science, which will be helpful for me to make this rocket come practical, as it is simple to build and easy to be, as all the materials can be easily be available. And yeah, thank you. Cool. Okay. Thank you very much. Yeah, okay. Stop sharing. Okay, thank you. I have presented my model meeting the criterias. Hope so well fitted in your criteria. Thank you, sir. Thank you, madam, to patiently listen to me. I'm grateful to Helium Learning app to give me such a great opportunity to build such a rocket and using such a great um, software, open rocket. It was a great experience as it has a best user interface and it gives nicely all the outputs easily to visualize and which can be practically made. So thank you to giving me such opportunity and such experience. Thank you, everyone.